So we're going to look at 9.1 and I'm going to share the screen. All right. Can you see that okay?
Yeah.
Um, are there any particular questions from here that you are wondering about?
Let me see. Sorry, my neighbor's dog is really loud.
That's all right.
Um, okay, number three. I was just going over a video on something similar to that.
Okay. So we have, let me write this information down. We have x equals 15 cos theta, y equals 2 sine theta, theta is between negative pi halves and positive pi halves. We're going to create an ellipse. Okay. Um, it kind of gives you the hint right there where you have that x squared plus y, I'm sorry, x squared over a squared plus y squared over b squared equals 1. So I'll stop sharing just for a moment. Let me go to my other camera. I'm going to turn my light on here. There we go. One thing you can do right now is just plug them in. That'll get you started. Um, there's a couple ways to do this kind of problem. You can construct it heuristically, or we can work it out in the fashion you see right here. I'm gonna, since I've already gone ahead and just plugged them in, I'm gonna go ahead and go with it. So I'll get 225 cos squared theta all over a squared plus 4 sine squared theta all over b squared equals 1. And I guess the trick is we want to come up with a value for a squared and b squared. And I'm just kind of looking at that.
Wouldn't it make sense to just be like a squared would be 225 and b squared would be 4, and then you'd have
Yeah,
cosine squared plus
yeah, that's
sine
that's
squared
exactly what I
equal.
was thinking. I was thinking about flipping them over, but yeah, that's exactly what you want to do. So yeah, that'll make it. We'll have a truth. So A is 15, B is 2. So you get cos squared theta over 15 plus sine squared theta over 2 equals, oops, yeah, that's right. Over 4, my bad. Actually, 15 squared and 2 squared equals 1. All right, so um, there you go. Let's see what did the question say. Let me go back to the question here. Oh, for Pete's sake. You're spitting on me.
I know the way they tried to, or they, in like the Get Help, and I think the other ones they like explained it, is that they wanted you to solve for cosine of theta and
Hmm.
then square, and then, substitute cosine theta with, whatever x over whatever it would be, 15, and
Yeah,
then do that squared plus the sine squared equal,
yeah, actually that works too. As I look at this, I'm thinking, I'm just kind of the wheels are turning in my head. You could do that. Is that what they were suggesting?
I think so. I think that's kind of like what they're getting at with that weird or that format that they do without actually telling you.
Yeah, so you get the you can use the Pythagorean identity, cos squared plus sine squared equals 1. And we have x over 15 quantity squared because that's what cos squared is, or cos is. And then y over 2 quantity squared equals 1. We get x squared over, well, 15 squared plus y squared equals 2 squared equals 1. So we basically get the same thing. We want it in the form with x and y. So this is the preferred form here. Okay. The bounds on theta. Okay, so right now, if theta is from 0 to 2 pi, we get the full ellipse. If we go from negative pi halves to pi halves, we're only going to get half an ellipse. And we should be getting this half. We're going to start at negative pi halves, come up to positive pi halves. So it'll be negative 2 to 2. And this will be a 15, and it'll be drawn in this direction. And you should be able to do this in Desmos. I'm going to bring up Desmos. I'm going to get that going. Give me a moment. Yeah, there we go. So I'm going to share my screen. And there you go. So you type it in using just parentheses, like you're typing a point. I typed in 15 cos t. So use t for theta, and then 2 sine t. And then you put the bounds in negative pi halves to pi halves, and you get the right half of the ellipse. Have you guys been playing with the Desmos on these guys?
Oh yeah.
Yeah,
Yeah,
I've
I've been
been
trying
taking
to.
yeah, it's a lot. It's a
taking
lot
a
of fun
lot
actually.
of
I'm going to show you since I got it on the screen here. I'm going to show you something kind of cool. Um, one of my favorite shapes. I'm going to go. You go cosine, let's say 5t sine 7t, and then you go from 0 to 2 pi. So you want the full, and you get a cool shape like that. You see that? Isn't that neat? These are called Lissajous. Lissajous. They're really cool shapes. So you can have a lot of fun goofing around with this stuff. I'm going to go ahead and stop the share. Actually, Grace, that was number 3. Did you have questions on any of the other ones?
I mean, I think at this point, going over any of them is going to be helpful to me.
Sure. Give me a second here. Bringing it back up. There we go. Um, Number 1, for example, how do you feel about that?
I mean, we could definitely work through it. I haven't had a lot of time for like doing the problems over and over yet.
Okay, I'll do number 1. I just copied it down. Um, So you're just going to eliminate the parameter. In this case, you just solve for t in the bottom one. So y minus 1 over 5 is t, and then you substitute it in the top one. And you just square it out. So it'd be y squared take away 2y plus 1 all over 25. And then if you write it out this way, you get that. Does that make sense? So eliminating the parameter is really just a matter of algebraically solving for it in one of the equations and substituting in the other.
Yeah, I feel like the hard part for these ones for me is like seeing a problem and knowing what to do, because then once I remember what to do, I can do it.
Yeah, sure, sure. There's like a steep learning curve. Um, Let me go back to the infinity. Did number two. Actually, it looks like number two and oh, two is a circle. Okay. Um, yeah, so when you look at when you okay, so the standard way to parameterize a circle is to use sine and cosine. And when you get to Calc 3, we do this a lot with parameterization of paths. I'm just going to verbally mention on number two. You see where it says x is 15 sine theta and y is 15 cos theta. That'll draw you a circle of radius 15. Actually, since theta is between 0 and pi, it just draws you half a circle. And it'll start at the top on the y-axis and go to the right. So it'll go clockwise. The typical parameterization is to use cosine for x and sine for y. And that draws it starting on the x-axis and going counterclockwise. And it'll all make sense in Calc 3 because that counterclockwise motion is preferred for a lot of problems. If you tweak the coefficients, if you compare 2 and 3, um, you see we have 15 and 2, then yes, you get an ellipse now. Um, and and then of course the bounds give you a part of an ellipse. For 4 with secant tan, well, I would do the same thing where you use the relationship, uh, the Pythagorean relationship would be tangent squared plus 1 is secant squared. And then do like we did previously where you set secant theta is x over 9, tan theta is y over 9, and then just pop them into that identity. And again, you'll get an equation, but then also graph it on Desmos to see what it looks like. Make sure you're doing it right. Um, I know I'm going kind of quick here. Uh, any questions on 5, 6, or 7? Do you have a preference on these three? Anybody can jump in?
I think 9.1 is all right for me, but
Let's take a look at, well, 5 will give you a circle of radius 15. You'll notice that you have an extra 1 and an extra 6. What you can do is you can move those to the left. So you have x minus 1 is 15 cos t, and y minus 6 is 15 sine t. And that actually gives you a circle, or in this case, part of a circle, um, with the center going to be at 1 and 6. So everything's been offset by those constants. That's the only difference. With number 6, well, that's an interesting one because we have the cosine is being squared, and see, let me think. Oh, you know what you could do is where you see cosine squared, you can treat that as 1 minus sine squared, and then since sine is x over 9, then just put 1 minus quantity x over 9 squared. That'll do the trick. Let's look at number 7 because this is actually one that comes up a lot in Calc 3. Suppose parametric equations for the line segment between 9 and negative 10 and 3 and 0 are given by x equals a plus bt, y equals c plus dt. We want to set it up so that at t equals 0, we get the first point, and at t equals 1, we get the second point. Now we're going to do this kind of heuristically here. And what I mean by that is we're just going to sort of beat it up with a stick. There's a more elegant way to do it when we get to Calc 3, but we use vectors. And I don't want to go, to have to explain that at the moment. So one way to do it is just simply build it kind of, I guess you could say logically. Oops. So if I set the constants a and c to 9 and negative 10, and then I have t over here, so I have some space for the coefficient. If I put in a 0 for t, that'll just drop out whatever's over here, and it'll give you 9 and negative 10. And then if I put in a 1 for t, I want to get a 3 for x. So I would have to take away 6. So minus 6 will do the trick. And if I put in a 1 for t here, I want to get 0 here. And so I would just simply, plus 10. And that's one way to do it. And there you go. That gives you the parametric equation for a line segment. This is for t between 0 and 1, this is a line segment. Okay. You're going to do a lot of this in Calc 3. You may even end up having me as your professor because I've got an online Calc 3 in the fall in the spring semester. So I might see some of you. But this is a common maneuver, so be aware of that, okay? Any questions on that one? Okay. Let's go back to the this is an interesting one. 8. Assume time t runs from 0 to 2 pi and that the unit circle has been labeled as a clock. I misspelled labeled. Match each of the pairs of parametric equations with the best description of the curve from the following list, enter the appropriate letter. So we want to go from 12 o'clock and move clockwise one time around. Again, a little insight for what you can do. You could actually just simply put these on Desmos, and I believe there's a way to do it so that it doesn't just plot instantaneously, but it plots using a slider. But I'll give you a general hint here. Whenever you start when x is cosine and y is sine, you always get a counterclockwise traversal, and it'll always start on the positive x-axis, so 3 o'clock. Whenever you go sine and cosine, so whenever you set x is sine and y is cosine, you always get a clockwise traversal, and you always start at 12 o'clock, which would be the positive y-axis. So number 2 should be A. Let's see, we want B, start at 6 o'clock and move clockwise one time around. It looks like this should do the trick right here because we're just negating. Yeah, that should do the trick. But again, you can plot it just to make sure. Let's do number C. Start at 3 o'clock and move clockwise one time around. If I do cosine and sine, that'll give me counterclockwise. If I do cosine and negative sine, that should give me, that should give me clockwise. So that would be C. 3 would be C. And I'm just kind of going through them kind of quickly. Do you want me to continue, or does that make sense?
I'm trying to put them in Desmos right now, as you're
Okay.
doing it.
You
I
know,
see the half circle, but then I guess I'm not understanding like, how I know if it's going counterclockwise or clockwise based off of looking at the graph.
yeah, give me a second here. I'm gonna play with it myself. There should be a way to do it with a slider.
I just set up a slider and you can get it to have the point just kind of like keep following the path over and over again and show you. I don't know how to. If you put
Okay.
the yeah,
Yeah, I got it actually. Yep, let me show you what I did. I put an A and I did cosine A of t sine of AT, and then I want to get it at 0. Okay, so check this out. As t goes from 0 to 2 pi, so I'm going to the right, I'm actually plotting it counterclockwise. Do you see that? Again, I went from, oops, I want to start at 0, and I want to go positive. So I want A to increase from 0 to 2 pi essentially. And that at least just gives me the clockwise traversal. That's what I want. Okay, this is kind of, it works. It gives me the order. Let's try another one. I'm juggling my, gosh darn it.
Yeah, that makes a lot more sense.
If I do, I'm going to try negative sine t, negative cos t. So negative sine t, and again, I just want to get it at 0. So 0, and I go with positive. I'm going slow here. So it's going to go, that's clockwise at 6 o'clock. And yeah, there we go. There you go. That's a nice way to confirm it. We actually have two parameters. We have an A parameter and a T parameter. Okay. Yeah, Desmos is your friend. Can you see my Desmos screen? I'm not sure. Can you see that?
Yeah,
Now, if I'm going to switch to Affinity, can you see that now?
yeah.
Okay, good. How about number 9? Let's take a look. This is kind of related to the earlier one. We have a circle here where the center is going to be 9 and 1, and the radius is going to be 3, because 3 squared is 9. And we set x equal to 9 plus 3 cosine t. Well, we can infer what y would be. It's going to have to be we're going to have to move that 1 over, so it's going to be 1 plus, then we want that radius. The coefficient in front of the cosine is the radius, so the coefficient in front of the sine is also the radius, so it'd be 1 plus 3 sine t. And as usual, you can double check that if you're not sure. Graph them on Desmos and see if you get that circle. And if it does, if you do, then you did it right. And then 10 is similar. We would set y equal to 6 sine t. And that'll give you the desired ellipse. And then in number 11, this is just goofing around. Um, I would just plot these on Desmos and then just see what picture you get. You get some really cool stuff. There's really no easy way to analytically untangle these. You could, in some cases, in other cases, forget about it. I think you would just need to graph them and see what you get. All right. Well, there was your very quick run through of 9-1. Let's take a look. 9-3, number 17. Let me share it. All the way at the bottom. 17. Use calculus to determine the exact y coordinate of the highest points of the curve r equals sine 2 theta. So all right, so this is number 17. So here, okay, I'm gonna go to my, sorry about that. Just jumping back and forth. All right, so you will see this in Calc 3. This is your this is your standard relationship to go between x and y and r and theta. So if you draw yourself a right triangle, r is the hypotenuse, x and y are the legs in the usual format, and theta's in the lower left corner there. And so this is the relationship you get here. So what you can do, so you take this polar form and you simply pop it in for these r's. Um, and we want the highest y value. So if you graph this, you know what? If you don't mind, let me go to Desmos
No, that's
and
fine.
yeah, let's do it in Desmos.
That's
Let me
kind of
get,
what I was trying to do. The issue I ran into with it was, and it kind of, I don't know, the get help thing, they do some magic. But I got to the point where it's like, okay, you find the derivative, dy over dx, I
yeah,
guess. And then whenever that is zero, that's when you have horizontal line, which would be either the highest or lowest point. But then like solving for theta in that case gives you the arctan of plus or minus radical 2, and then you have to
yeah,
plug that into like cosine squared of the arctan of square root of 2. And
yep.
I
That
mean,
sounds about right.
it was insanely messy. And then when they did it, they're just like, oh yeah, well if you just substitute in arctan of radical 2, you just get radical 3 over 3. I'm like, what?
Right. Yeah.
Where'd you get that? And so that's
Yeah,
confusing.
we'll work that. I'll show you. Okay, first order of business is that get a sense of what you're playing with. Here is the picture. All I want to see is what the picture looks like. Can you see that there? It's like a four-leaf clover.
Mhm.
Now, you in Desmos, if you specifically use R and theta, you just type THETA and it'll give you the theta symbol. It'll give you the polar graph. And I'm I'm pointing at the top right, the top left, and the top right here, and um, I want a zero slope tangent. So I want to get dy dx to be zero. Okay, so I'm kind of writing some stuff down as I look at this. Um, I'm gonna stop and I'll come back to this. So I want to get dy dx equal to zero because according to the graph, it has kind of this flower shape. And I want that to happen. Okay. And so what I do is I go, so dy over dx would be dy d theta over dx d theta. Now, we don't need to mess around with dx d theta because I just want to get dy d theta to be zero. So I need to take this derivative and I'm going to have to use the product rule. So it's going to be first, derivative second, plus second, derivative first will be 2 cos 2 theta. And I need to set that to zero. And okay, I can see what's going to go on here. what we got a little problem here. We've got kind of like inconsistency in the argument. So I need to replace, see, sine of 2 theta is 2 cos theta sine theta. And then of course that cos theta gets multiplied. And then I'll put the 2 out in front. And then cos 2 theta is, there's a couple ways. I'm going to use the 1 minus 2 sine squared theta equals 0. Now it is messy. I don't deny that at all. You have 2 cos squared theta sine theta plus 2 sine theta, take away 4 sine cubed theta. Oh my God. All right, I'm just going to go with it. This cosine squared can be taken as 1 minus sine squared theta. So let's go ahead and do that. And I'll distribute both ways. I'm going to have 2 sine theta, take away 2 sine squared. Actually, it'd be sine cubed theta. This will be 2 sine theta. I'm just copying down. Oh my gosh. You still with me on this? So
Yeah.
actually,
Yeah.
looks like it's going to clean up. I'm going to get negative 6 sine cubed theta plus 4 sine theta equals 0. Let's see. I can factor out a sine. Yeah, I can reduce these. This will just be 3 and 2. So I'm going to factor out a sine. And I'm going to get negative sine, negative 3 sine squared theta plus 2 equals 0. All right, I think we got something now. All right. Let me just kind of reiterate what I did here. I took the y, which was sine 2 theta, sine theta, and I took its derivative, dy d theta, as the product when I set to 0, and I just have to flesh the whole thing out into, really, in this case, I just want them in terms of just sines of single theta. So I was using some identities here to do that. And I hope I didn't make any mistakes. I think I'm okay. All right. So sine of theta gives you 0 when theta is 0, pi, and 2 pi. This is sine squared theta. What we do is we set this to 0. Let's see, sine squared theta, it'll be 2/3. So sine of theta is square root 2/3. Okay, I think this is where you got, right? Plus or minus, my bad.
I didn't even quite get to. I just put into Desmos because I didn't know how to do that on paper. But when I got to a point where I was taking the cosine of the arc tangent of radical 2. I was like, nah, I'm just gonna put that in the calculator and let that do the math for me. But in their step, they're like, oh yeah, so you have arctan of radical 2, plug it in, and now you just, through the magic of math, you have radical 3/3 or whatever. And I was like, okay,
Yeah.
I don't know how they got to that through that, but
Um, I'm looking at this here. I kind of dropped the plus and minus for a moment. I I hope I didn't make a mistake. I'm pretty sure I didn't. So I get this crazy value. What did the question want? I spent so long since I looked at it. The question wanted, what's the y coordinate of the highest point on the curve? Okay.
because then you get the theta at which it's the dy over d theta is 0, but
Oh,
now you need to find what
yeah.
the y value is at that point. So you have to plug that into the original mess.
Well, you got theta is inverse sine of rad two thirds, and the y value here is what you see right there. I don't see why we can't just plug it in. So, oh my God. Yeah, all right. This guy's gonna cause trouble still, so I'm gonna replace it. It's sine of two theta is two sine theta cos theta, so that's the two sines make a sine squared. So if I plug in inverse sine of rad two thirds here in the sine, sorry, it gets messy. They'll just cancel. And you get two, and then this just squares, so two times two thirds is four thirds. And then this is multiplication, so we still have this thing to worry about. And all right, I'll show you what to do here. What a problem. All right, so here's the idea is that I'm just going to use a temporary variable t. T is the sine inverse of rad 2 over rad 3. That means sine of t is rad 2 over rad 3. That means if I draw a right triangle with theta tucked in the corner, or t, my bad, I want to use t just for a moment. It'll be rad 2 on the opposite, rad 3 on the hypotenuse, because sine is opposite over hypotenuse. And then I need to get the leg here, and I just use Pythagorean, so I'll call it a. So a squared plus rad 2 squared equals rad 3 squared. So a squared plus 2 equals 3. So a squared is 1. So a is 1. And I'm ignoring the negative for a moment. So a is equal to 1. And so what you do then is that you say, well, what's the cosine then of this? This is basically an angle. So the cosine would be 1 over rad 3. And that should be the correct answer, I hope. Again, that's a lot of gymnastics there. Did you see how I decomposed this?
Yeah, I did not, yeah, think about using that kind of strategy to solve
The trick to remember
trigonomic
is
functions of inverse trigonomic functions.
these are actually angles. Whenever you see an arc sine, arc cos, arc tan, you're actually looking at an angle. So if you call it an angle, and I didn't want to use theta because I'm already using theta, didn't want to mess around with. So I just gave a temporary variable t. And so I drew a triangle and I just tucked t in the corner here. And I know that the sine, so I take sine of both sides, the sine of an angle is opposite over hypotenuse. So I just label opposite and hypotenuse and then use Pythagorean to get the other leg. And then I look at the cosine on the outside and just say, okay, what would the cosine of this be? Well, it'd be adjacent over hypotenuse. And there you go. I'm dying of curiosity. Did I get that right?
I just double checked you. You did. That
Oh,
was correct. They give it in a slightly different form. They do like
oh yeah.
4 radical 3 over 9, but yeah, it's
Yeah. Oh wow. I even surprised myself. All right. Huh. Well, that was a lot of fun. All right. Does that help you guys? Hopefully you still want to major in engineering after all this, right?
that that
You rarely
definitely
see
helped.
problems like this the higher up you go. This is kind of really testing just your I guess you could say your mechanical skills. If you can walk through a problem like this, then you really have a handle on your trig.
Is this something that we might see on the final?
Yeah, anything from the homework on chapter 9 is fair game.
I know you mentioned
Uh,
earlier that, oh, sorry,
Go ahead.
that the final is kind of more like a test 3 than it is like a final.
Well,
but I'm
Yeah,
obviously not like only.
yes, it's mostly covering the new material. There will be a couple earlier questions. Final's still being kind of composed, so I'll be sending more information probably by tomorrow. I'll be sending you guys all an email about what to expect. All right,
Are you able to go over the last problem of 9.2?
sure, let's take a look.
I just didn't know how to set it up because I had the line where it's y equals 50 over 7.
Give me a moment here. Oh my Lord. All right, let's take a look at that one. So find the area bounded by the curve x equals t plus, I'm sorry, oops, minus 1 over t, y equals t plus 1 over t. So this creates one graph, and then the other graph is y equals 65 over 8. Okay. I'm thinking about how I'd want to approach that. Yeah, first thing I would do is, gosh, I would actually take these two guys and relate them. So, because y is also known as t plus 1 over t, so I have t plus 1 over t. I'm sorry, can you see me okay?
Yeah.
All right. Always remind me because sometimes I start doing a question and I forget what I have actually on the screen. So anyway, I can multiply through by t. Actually, I'll multiply through by 8t, and that'll get rid of the fractions. I'll have 8t squared plus 8 equals 65t. So 8t squared take away 65 plus t, my bad, plus 8 equals 0. And then actually, you know what? 8 and 6. This actually factors. If it didn't factor, or if you weren't sure, just put it in the quadratic equation and it'll give you the numbers. Let's see, we have 8t and t, 8 and 1, and minus. That should do the trick. I mean, yeah. Oh, okay, that worked out good. I suspected that 65 over 8 was chosen so that it would make this work out nice. So we get t is 1/8, t is 8. So these are your bounds. Okay. All right, so when we integrate, we have normally do y dx, which is what you've been doing all along since Calc 1. But now what we do is the dx actually it gets derivative. So the dx is going to be over here. It'll be 1 plus 1 over t squared dt. Okay. I just took the derivative up here. And then the y, okay, the bounds are 1/8 and 8. And the y, well, we want top minus bottom, so it's going to be 65/8 minus the bottom. Let me pause there. You guys catch that maneuver? This is top minus bottom. And I'll be honest, if you don't know which one's which, just pick one, go with the math. If you end up getting a negative answer, that just means you picked them in the wrong order, so just negate the answer. So normally when you integrate, it is an integral y dx. Y is some function of x. Normally we would write f of x dx. But now we're doing it in terms of t, so we have the y equations in terms of t here, top minus bottom. And dx, well, we have to turn that into dt, so we take the derivative up here, throw it down here. And really at this point, it's just a monster algebra question. So I'll pause here. Does that make sense? This is really the meat of the question right here. Do you see how I was able to formulate it all together? Are there any
Yeah,
questions?
I think my issue was just trying to find the bounds.
Okay.
Yeah.
Um, yeah, I think in this case, this was the only logical. This was like the most logical thing you could piece together. Take the two expressions in y and set them equal. And you'll get t bounds. And I mean, if you really wanted to, you could plug those t bounds into the x as well. You don't need to, but you would. Okay. Um, the rest of the question is just monster algebra. It's not going to be pleasant. You're going to distribute this expression through this expression. It's not difficult. It would be 65 eighths t plus 1 over t squared. Take away, and then these two guys multiply. Actually, that's a 1, 1, 1. It's my bad. It's a 1 plus 1 over t squared. And 65 eighths plus 65 eighths t squared. And then here you get t plus 1 over t plus 1 over t plus 1 over t cubed. Oops. Sorry, hold on. Yeah, I want to make sure you can see that. I'm not going to go all the way to the end. I'm just going to try to simplify this a tiny bit. So we have yeah, you got a lot of t's. You got a t to the -1, a t to the -3, and a t to the -2. So you just integrate all these the usual way, and then pop in the bounds. Do you want me to complete it, or are you good to go?
Yeah, that's fine. I just curious of how to set up to find a bounds because I had one where the get help me kind of got me confused, but the way you kind of explained it kind of makes sense.
The get helps kind of a variable. Every professor has their own technique, and sometimes frankly, when I look at a problem like this, I don't really I don't like go from a formal plan. I just kind of jump into it feet first and go hope for the best and hope it works out. It looks like it's going to work out. It's not going to be pleasant, but hopefully this made sense. Yeah, this would be how you find the bounds right here. All right. It is 7 o'clock. I can take maybe one more question since we got a late start. Does anybody have like a quickie we can knock out in about 5 minutes?
Maybe 9.4 number 3, if you think you can do that in 5 minutes, maybe.
All right, let's take a look.
Let's see. I don't know
Nine
how
four number 3.
complicated it's supposed to be, but
Hopefully I can do it in 5 minutes, right? 9 4 number 3. Find the area enclosed by one loop of the lemniscate. What do we got going on here? I'm 9, 4, number 3. If the function is r squared equals 9 cos 2 theta, and if you plot it, you actually get what looks like an infinity symbol. It's called a lemniscate. Okay. So what you need to do, the standard area formula, because when you decompose the shape, you're actually decomposing in little triangles. I won't go through the derivation. It's integral. So there's a half on the outside, a to b of r squared d theta. Oops. Well, you get a little lucky here because um, you already have the function in terms of r squared, so you just need to make that replacement. It'd be 9 cos. In fact, you can bring the 9 out in front. Cos 2 theta d theta. So it's actually going to be a fairly easy integral. The tricky part is what are the bounds? Okay, you need to figure out what theta generates a, I guess you could say a loop. Well, you want to find out when r is 0. So when r is 0, you're at the origin. So you set 0, well, r to 0, r squared, I guess. 9 cos 2 theta. So divide out. Well, the cosine is 0 when theta, actually, I didn't want to do that. The cosine is 0 when theta is pi halves, 3 pi halves, 5 pi halves, etc. But we just need 2. So cosine of pi halves is 0. So we have a 2 theta here. So it's actually 2 theta equals pi halves or 3 pi halves. So that means theta, if I divide out by 2, is pi over 4 and 3 pi over 4. So those become your bounds. Okay. Now, let's be honest here. At this point, you could feed this in as an integral and get a decimal value, which would probably be acceptable. Because on the test or on Desmos, we usually there's really no way to kind of control that. But if you worked it out, it's not that bad of an integral. It's just going to be, so we have 9/4 sine 2 theta 3 pi over 4 over pi over 4. And when you plug in 3 pi over 4 here, you get 3 pi over 2. Sine of 3 pi over 2 is -1. And then sine of pi over 4, 2 over 4, it's going to be pi over 2. It's going to be 9/4. So you get -9/4 minus 9/4. So let me get a negative value. Did I do something wrong? Let me double check myself. No, I did it right. All right. I think I see what happened. They actually went from negative pi fourths to positive pi fourths. All right, fine, whatever. I actually, you know what I did? I did this guy back here. All right, just drop the negative and you're happy. All right.
Okay. I think I got a little tripped up or a little confused, or I don't know. I got too focused on the r squared and tried to like isolate r and then work from that. And I kept ending up with pi over 2 as the bound, like negative pi over 2 to pi over 2, which was obviously just giving me 0 because that's like the whole graph.
Right.
But yeah, I guess I didn't think. So setting, or not setting, but I guess expecting r to be 0 because you know that that's where it intersects is kind of another way to solve for bounds, is to be like, okay, well, I know when r is 0, then those are our two bounds.
Right.
Okay.
Uh, Here, there's kind of a style issue too. Whenever you're doing like these kind of loops, you generally are looking for where the loop starts and ends for once. And you'll notice over here, I did it in quadrants I guess not, it'd be 90 degree and the 270 degree angle. This will work. This actually gives me the back half, I realize now. No big deal. It's symmetrical, so I'm okay. If I had gone from negative pi halves to positive pi halves, so I had negative pi halves, positive pi halves, then I would have negative pi over 4, positive pi over 4, and that would have given me the positive version. So I don't worry too much about the sign. As long as I do all the other stuff right, you get kind of like a negative area, and kind of in a sense, it's like R is negative back here. It's a weird, it's like you're going backwards, but it still gives you the same number. You just sort of drop the negative. It would have been cleaner to use negative pi over 4 to pi over 4. That's a style consideration. Well, guys, I'm gonna go back to my screen here. Got my pirate regalia on. I want to wish you all the best of luck in your plundering on the high seas, and try to stay away from those ships from France. They're nothing but trouble. But in all seriousness, good luck on the final. And I will be sending more information about the final. It's in terms of its actual size, it's the same length as a normal test. And please remember, I'm offering that grade reweight that I posted in the announcements. I will do that after the final. So everybody will benefit. And so basically I take the best of your 3 tests and grade it at, or weight it at, I think it's 35%. I think it's 35, 25, 15. And that way your best score gets weighted the most, your worst score gets weighted the least. And hopefully that will help everybody out. It will. Everybody will get some benefit out of that. So hopefully that will help you out and bump you up a half grade or something. Alrighty. Well, it's been a pleasure working with you guys, and just kind of hang in there for a few more days and we'll be done with this. I'm going to go ahead and end this meeting.